This is the first public lecture for 2010 for the Institute for Sustainable Solutions at the University of Sydney. And it's my first event since being appointed director of the Institute late last year. There's a difference, I think, between climate science and climate change. Climate change has very rapidly moved from a science issue to a social and cultural issue, upon which I think we hang our biases, our worldview and our hopes and our fears. Tonight you'll hear from a leading climate scientist about the science, about what this man has studied for his entire career, what he understands by the science and what is contained in the IPCC reports about the climate science. How you react to that and think about climate change, I think, is an issue for you and for our policymakers and politicians to think carefully about. But I'm delighted to welcome to the stage to talk to us about climate science, policy and potential solutions, Professor Michael Oppenheimer.
Thank you. It's been a pleasure to be here, and it's very interesting coming from a country, the United States, where the climate issue truly is on the back burner, far behind the concern about our economy and also the healthcare issue, which we seem incapable of dealing with. And it's interesting to come here where there's still a rather intense discussion going on about climate change, intense but not always enlightening, I'm afraid. And what I'd like to do tonight, is to go back to basics, go back to the basic science, look at the key elements of the problem, in hopes of shedding some light, maybe contributing in a minor way to quieting the discussion a little bit and leading it in more rational directions, and then toward the end tease out what I think are the policy implications of all of this. So without further ado, and hoping that I don't have a nervous breakdown myself in operating the computer, which sometimes happens, let me talk about where this problem comes from and what it really is about. So certain gases that exist naturally in the atmosphere, called the greenhouse gases, are transparent to sunlight, which comes through and warms Earth. But these same gases trap heat that would otherwise escape into space. That's what we've got here, sunlight coming through, warming Earth's surface, trying to radiate that heat back into space, but some of it here being trapped and returned to Earth. That's the greenhouse effect. It's been understood for about 200 years, and it's a good thing. Without the greenhouse effect, Earth would be about 30 degrees Celsius colder than it is. It would be a frozen desert. Life as we know it would never have evolved, and we all wouldn't be around here to have these terrible arguments and discussions about what to do about global warming. We can find out a lot about these greenhouse gases by going to the poles, the big ice sheets in particular in Antarctica and Greenland, where scientists go and they put up installations that look like oil derricks. They drill down and they retrieve sections of ice cores that, when you add them up, are, can be up to a couple of kilometers long of ice. And they take this into the lab, and under very clean, pristine conditions, they shave the ice cores. And in those ice cores are little air bubbles. The reason the air bubbles are there is because when the snow fell that formed the ice, before it got compacted, little bits of air, if you imagine a snowflake. Ever seen a snowflake? I guess some of you probably haven't, but I've seen too many of them this winter. And it traps the air bubbles between the points. The air sort of finds itself and consolidates. Little pockets of air consolidate into bubbles. And then when the whole thing freezes, the bubbles are trapped, and then that's the oldest ice we have is almost 1 million years old. The oldest ice we've analyzed is about 800,000 years old. So along comes Homo sapiens sapiens at the end of this long journey, drills up these ice cores in his brilliance, and finds these bubbles, which are an archive of what the atmosphere looked like 100, 1,000, 10,000, 100,000, as I said, up to 800,000 years ago. And so from that archive, we can tell something about the history of carbon dioxide in the atmosphere. And focusing here on the last 10,000 years, here's 10,000 years ago, here's today, this is the level of carbon dioxide in the air samples, the samples of the old atmosphere coming up to today. And on this rather contracted scale, you'll see the carbon dioxide levels were fairly constant for most of the last 10,000 years. And I use 10,000 years because that's the period since the last major glaciation of Earth. And we know there haven't been major climate swings over that period, not on a global scale anyway. And we come to here, and all of a sudden, the thing takes off like a rocket ship. And if you expand the scale and look at only the last 200 years or so, here's 1800, here's today, you see that again there's just a little bit of an increase here, probably due to deforestation and a little bit of fossil fuel burning, and then the curve takes off. And this is a unique phenomenon, and there are very few things in this problem I'm going to say I'm certain of, but one thing I'm going to say I'm certain of is that carbon dioxide and the levels of other greenhouse gases have changed, and that change is due to human activity. We just don't have any doubt about it. There's several lines of evidence that lead in that direction. The buildup is connected primarily, but not entirely, with the burning of fossil fuels. And I want to say there are other greenhouse gases, both naturally and due to the human addition to the atmosphere. Methane is an important greenhouse gas. That's, you know it perhaps as natural gas or swamp gas. It has many natural sources, but it also has human-made sources. If you open a coal mine, some methane leaks out, for instance. Nitrous oxide, which you would know of as laughing gas, has many natural sources, but it has human-made sources, for instance, when you spread fertilizer in agricultural production. So, and there are a few other gases which are worth paying attention to, but I don't have time to go into it here. And here you see the total, since 1970, the bar charts indicate the total global emissions of all the what are called the long-lived greenhouse gases, the ones that hang around the atmosphere for at least 10 years after emission. There are some short-lived ones as well. And you see there's been a very steady increase. The pie chart shows how much each of these gases contribute to the current global warming effect in the atmosphere, essentially. And you'll see that carbon dioxide from the fossil fuel sector is about 60% of the current contribution. There's also a big chunk here, about 15 to 20% of carbon dioxide and of the greenhouse effect comes from cutting and burning of forests in the tropics in places like Brazil, for instance. What is the industrial source of these gases in terms of, the machinery that it comes from? Well, the biggest growth is in the electric power sector. Here's 1970, here's today. And also transport, particularly road transport, but also into air transport is increasing rapidly as well as a source of these gases. And the final point I want to make on the emissions is that this is no longer a problem of the big developed OECD economies like EU, Europe, EU, Australia, the US, and Japan. It's now become a problem which is being dominated by the developing countries, the non-OECD countries, which are the red bars, the developed countries are the blue bars, and you can see in recent years the red bar has gotten bigger than the blue bar, and we see that that in the future the ratio is expected to increase. So that this one lesson to take away here is if you think you want to solve the greenhouse gas problem, you simply cannot do it without engaging the big developing countries like China and India. Now, okay, I've shown you that the greenhouse gases are increasing. Why do we think, and I argued that greenhouse gases warm Earth, so the greenhouse problem arises because as humans add more greenhouse gases to the atmosphere, they add a greater and greater potential to warm Earth. But how do we know that some warming actually, what's our evidence that this has actually will actually cause warming in the future? And here I present more evidence from those ice cores. The red is carbon dioxide. Over time, going back 800,000 years from the ice core taken from near the South Pole. And the blue is methane levels, and the black is the temperature of the atmosphere from which the snow fell that consolidated into the ice cores. If you want to know how we know that, it has something to do with the isotope ratios in the water in the ice. We can talk about it later. It's a complex detail. But you notice very interestingly that both the carbon dioxide and the methane and the temperature above Antarctica went up and down naturally over time. That tells you two things. It tells you, first of all, and by the way, the ups and downs are very closely correlated. It tells you two things. It tells you there's something that can change the climate naturally, at least over very long periods of time. And we're pretty sure we know what that is. The attitude of Earth's orbit relative to the sun changes over time. That changes the amount of sunlight reaching one or the other hemisphere. That instigates or triggers some warming of the Earth and also triggers a change in the amount of greenhouse gases in the atmosphere. And then the amount of greenhouse gases further amplifies the warming. There's a consistent picture, although we're not 100% sure of all the intermediate steps, that you cannot explain the changes in the Antarctic temperature between, say, a warm period like this one we're in now, or the previous one 125,000 years ago, and a cold period, which in the northern hemisphere we know as the ice ages, without invoking the change in the amount of greenhouse gases. And if you count the amount of warming that should have occurred due to the carbon dioxide building up and the methane building up, it's consistent with the amount of warming that occurred during one of these transitions from a glacial period into an interglacial period. So there's a picture that fits together there, and that gives us confidence that climate that builds up in greenhouse gases will cause a change in the climate. I want to say, you might ask, all right, so if the climate changes naturally, why are we worried about a human-made addition? It's because although these swings are pretty big, they happen very slowly. And we're in the middle of an interglacial or warm period here, and because we know quite a lot about the orbit of Earth around the sun, we can say with some confidence that we would not be falling into another ice age like this for something like 10, 20, 30,000 years, but we will change the climate due to global warming, due to the human-made buildup of the greenhouse gases over the course of the next 100 years if we don't stem the emissions. The other thing to notice here is that this is today's level of carbon dioxide, and it's about 30% above any level recorded in those ice cores for the last 800,000 years. And there is other evidence that suggests that actually carbon dioxide is now higher than it's been in several million years, and several million years ago, Earth was a significantly warmer place. So this fits together as a picture which suggests strongly that we have already primed the atmosphere here for a significant warming. Now let me step back a minute and give you some generalizations about what we know. Very important, and a thing that distinguishes this problem from nearly any other political problem that our leaders have to deal with, if you think of it as a political and not just a scientific problem. These emissions are very long-lived. Some of the carbon dioxide that was emitted from the engine of the first automobiles that were driven over 100 years ago is mixing through your lungs as you sit here and breathe. Some of the carbon dioxide we emit today will still be in the atmosphere, about 20% or so of the emissions 1,000 years from now. And unless we're clever and we find some way to suck it out of the atmosphere, which is physically possible, but at least today incredibly expensive. So the decisions we make today to control or not control emissions will have implications for people living on the planet for many, many, many generations to come, and are, at least from today's point of view, effectively irreversible. And we also know that climate changes are already underway and that more are to come, even if we start reducing emissions now, and I'll show you why later. And this has all been known for some time. The recent developments of the last few years have amplified scientific concern about this problem. First of all, as the question of climate change has focused the scientific community, we've started also paying attention to the question of how human beings are able to adapt to the risks involved with the kinds of climate extremes that global warming is expected to bring. So, for instance, it's very likely that as the world warms, there'll be more intense heat waves. How good are we at adapting to heat waves? Much worse than we really should be or could be, and I'll give you an example later. Heat waves kill people. People die in heat waves. We could avoid it. We're not very good. We don't live up to our potential to adapt. In my country and in the north of this country, tropical storms are a big issue. Hurricanes in the Atlantic basin are expected to increase in intensity, though not frequency, in a warmer world. And we know from the examples that we've had in the United States in the last few years, most notably Hurricane Katrina, which probably had nothing to do with global warming, but provides an analog for what we might have to deal with more in the future. We know we're not very good at anticipating, even with a storm, that everybody was saying for several decades would eventually show up and do severe damage to the city. And we sort of sat there and did nothing about it. So there are demonstrated limits on our ability to adapt to just the kinds of extreme events we are expecting more of. And when one looks at all the full range of not just extreme events, but all the impacts of global warming, which I'll go into in a minute, there's become sort of a consensus in the scientific community. I want to be careful about it. It's not a full consensus, but it's sort of a best estimate of where the risks really start to pile up. We don't know exactly what happens at what level of warming, but we have a general idea. And if you put down what we know, and I'll show you later, we see that there's a kind of concatenation of risk if you raise Earth's temperature above about 2 degrees warming. And the governments have recently taken up this as a preliminary idea of a target for global warming policy, that Earth shouldn't warm more than a couple of degrees at most. And I'll show you later that it's actually unlikely we're going to meet that target, unfortunately. And finally, the window of opportunity to avoid such a warming is closing. And it's going to be difficult primarily because we're rather late out of the box and starting to do something about the problem. This is a little bit of a complicated graph, but it goes to the point I made about the long lifetime for the accumulation. I don't want to go into great detail, but if you just let emissions zip up like this curve is the business as usual curve for emissions without doing anything to stop them. Then in the year 2150, now is that 2150 or 2100? It's 2100. You all of a sudden bring emissions to a halt, stop everything, shut down every factory, throw all the automobiles in the ocean, stop deforestation completely. Impossible to do, obviously. No carbon dioxide emissions. You notice that blip still keeps carbon dioxide emissions above the pre-industrial level, which is way down here, way out for the full millennium. In other words, there is no way that we have today to practically reverse levels of carbon dioxide, and the natural processes like dissolution in the ocean take it out of the atmosphere very slowly, so that the bulge created by industrialization, even if we managed to get off fossil fuels by the end of the century, would leave a hangover which would take the full millennium to disappear. It's in that sense that I'm indicating that this is effectively, there is an irreversibility in the problem. So now, those are the general principles. Let's talk a little bit about what we are able to see today in terms of actual changes in the climate. This is the Earth's temperature data taken by thermometric readings, thermometers, for the last 150 years or so. And you notice there's a lot of jiggle-jaggle in the curve, but in general, Earth has been warming. And so, but I want to, be clear that in the process of there being an overall warming trend, there are periods where Earth's temperature has actually stopped warming or even declined for short periods of time by a few tenths of a degree. The overall warming is about 3/4 of a degree Celsius. So you should be aware if you hear statements like, well, it hasn't warmed during this decade, well, so what? That's happened many times in the recorded, in the temperature record, but it doesn't change the fact that there's a long-term upward trend. Similarly, the warming of Earth is associated with an increase in the sea level. This is probably the most, in my mind, the most outstanding and troubling impact. And that happens for several reasons, 3 mostly. Number 1, mountain glaciers, which are shriveling away almost everywhere, and which I'll show you later. When they melt, the water has to go somewhere, winds up in the ocean. Number 2, water, like most fluids, when you heat it, it expands. So just the volume of the ocean, even if the mass didn't change, is increasing. And thirdly, we've discovered fairly recently that the major ice sheets, parts of Antarctica, parts of Greenland, are frittering away at the edges. The peripheries are starting to melt, and there isn't enough extra snowfall happening in the middle of the cold ice sheets to compensate. So in general, sea level has been rising rather steadily for the last 150 years or so. There is some question about when the sea level rise actually began, but it's fairly clear that it accelerated sometime during the era of the buildup of the greenhouse gases. We know this is now certain. I mean, we know this from several different instrumentation methods. They used to measure sea level by putting little flotation devices on the ocean, and there was always some doubt about how accurate that was because you couldn't put flotation devices along all coastlines. There wasn't global coverage. You may see this little red curve here, What happened about 15 years ago is we finally sent a satellite up which could get true global coverage of the oceans. And you'll notice that the satellite indications of how fast sea level are rising were smack on the curve, which had already been determined by the flotation devices or tide gauges. So we now have a very comprehensive picture of sea level rise on a global basis. And finally, the snow and ice lines. You know, down here you don't have to think about them, but in North America we think about snow lines. If you drive a stake in the ground in the middle of North America, at the coldest part of winter where the snowpack has advanced as farthest, it's deepest into the middle of the continent. And if you marked every year where that edge was, it would jump around a little bit, but the trend basically is a gradual decline in the snow-covered area. So snow, ice, temperature, sea level, snow, and ice are all changing in a way that's consistent with the buildup of the greenhouse gases. Extremes of heat are on the increase. Extremes of cold appear to be on the decrease. Rainstorms have gotten more intense. When it rains more powerfully, and the reason for that is that a warmer ocean yields more evaporation of moisture into the atmosphere. But in areas that don't have access to that moisture at a particular time of year, there's been apparently a greater tendency for drought simply because the soils are baking out more. As I said before, tropical cyclones appear to be increasing in intensity, although not frequency, with more Category 4 and 5 storms and less of the Category 1 and 2. And the oceans are slowly acidifying. They're acidifying because carbon dioxide, when it dissolves in water, turns the water slightly more acid than it was previously, and that's not good news for shell-forming creatures like corals, which essentially will either suffer greater dissolution or won't be able to form in the first place. And there's grave concern about what that means for the marine food chain, although a lot of uncertainty, too. We don't know the biological effects very well. So starting with here, it's certain that temperature is increasing. It's virtually certain that sea level has increased. It's virtually certain that ice and snow is shriveling in extent. It is also likely, although not certain, that heat waves have increased and that extremes of cold have decreased. It's more likely than not that rainstorms have increased in intensity and that drought has increased in areal extent. And it's more likely than not that tropical cyclones are getting more intense. And it's certain that acidity has increased. So I'm trying to be careful here. Not everything we know about global warming do we know with the same degree of likelihood, with the same degree of knowledge. And we try to be very careful to distinguish between those things we're sure of, like that Earth has warmed, and those things we're not sure of, but we have some confidence in, like the changes in tropical cyclones. Mostly, if a scientist tells you he or she is sure of something, you ought to cross-check, because there's a limited number of things that we really are 100% sure of with this problem. One of the things that seems to be happening pretty surely is that the Arctic ice pack is shriveling. The Arctic ice pack is critical to Earth's climate because when there's sea ice, it reflects sunlight and it kind of helps the Earth stay cool. And as the warming melts the sea ice, it adds to the warming in what's called a positive feedback. The red, which I hope you can see, I can't see it very well from here, is the extent of the average of the Arctic sea ice pack in 1979, which was the beginning of satellite observations. The white is where it was in a recent year, 2003, having shrunk by about 25%. This is the curve which shows the extent, the aerial extent of the Arctic sea ice. And you notice it bounces around quite a lot, just like, you know, the temperature does bounce around too. And you have to be careful. You can't be taken away with the drama of one of these peaks. If you were in this year, I'm sure some people were claiming, don't worry, the Arctic ice is recovering. And when we were in this year, a lot of people got worried that the Arctic ice was about to disappear completely. But of course, it recovered here. But what it recovered to was a downward trend line. The natural level would be up here somewhere. This is partly due to the buildup of greenhouse gases in the Arctic warming and partly due to some circulation changes in the Arctic, which might or might not have anything to do with the greenhouse effect. But the trend is clear. Arctic ice is shrinking. And probably by the end of this century, if these trends continue, we'll simply not be there anymore. It's well established that mountain glaciers are disappearing. And here, each of these curves is the average length of studied mountain glaciers from different areas like the Atlantic, the Alps, the Southern Hemisphere, Asia. There was a big brouhaha about a mistake having been made by IPCC on the future of the Himalayan glaciers, and it was a grievous error. But on the other hand, it didn't change the picture that the Himalayan glaciers, along with the rest of the mountain glaciers on Earth, are actually shrinking in extent. They will, however, not completely disappear by 2035, which was what the mistake said. And here, this shows you the area of the areas of Earth that have been drying over this century. This is a complicated picture, which I won't try to explain in detail. The Palmer Drought Severity Index is one of the ways of measuring drought extent. And the blue are areas which are relatively moist, the red are areas which are relatively dry. So what this curve means is that over time, there's been a shift from relative moisture to relative dryness during this century, during the last century. And the red areas are the ones that have gotten drier. It doesn't mean they're all in drought. So for instance, Australia doesn't mean that the whole continent is in drought, or it means that over that period, there was a spread in the areas which were dry relative to the areas that were wet. Species are moving in response to all this. This graph shows the distribution of certain species in Europe. This is the level that they used to live at in the period 1905 to 1985. This is the levels they lived at in the period, the subsequent 20 years. You notice that if you put all the dots together, there's a subtle effect. If the straight line that goes like here, the 45-degree angle line, would be where all the points would lie, or equal number above is below, if nothing had changed. But you see there's a subtle increase in the density of points up above the line, which strongly suggests that things are moving up the mountain, essentially. Species are moving to higher elevations, and that's because it's cooler at higher elevations. That's why they find the climate that they're adapted to living in. But you have to ask what happens when they can't go to higher elevations, or in the case of the polar bear, what happens when they can't go to higher latitude. There's simply no room left for them to go anywhere. I don't think polar bears are going to go extinct because they're going to die outright from the warming. I think that the last polar bears will be saved by putting them in zoos, or they will interbreed with the brown bear, which is a dominant species in that part of the northern continental areas, or they'll be shot as they rummage through garbage in places like Churchill, Canada. So that is the story on what has started to happen already. Now let me make a shift and talk a little bit about what we expect to happen in the future.